So the last thing I want to talk about is just a little bit about, a little more about rotational kinematics and dynamics. Okay, so just remember that for our linear motion, we have position, velocity, acceleration, force, mass, just going through my chapters. For kinetic energy, for example, we have 1/2 mv squared, and we have momentum. That pretty much covers it. And the rotational equivalent is theta, omega, alpha, torque, moment of inertia, and there's a rotational kinetic energy, which is 1/2, whoops, not 1/2 m, but 1/2 I, moment of inertia, omega squared, and for momentum, there's angular momentum. So those are the rotational equivalents. Actually, the kinetic energy is a little bit different. Something can have, well, actually, something can have both kinetic, never mind, it's not really different. Something can have both kinetic energy, rotational motion and linear motion. But I guess my point is that's not really a variable replacing a variable, because the m's replace the i's, replace the m's, and the omegas replace the v's. So kinetic energy doesn't really belong there. That's just sort of like saying F equals ma, so therefore torque equals I alpha. Kinetic energy equals 1/2 mv squared, so therefore kinetic energy is 1/2 I omega squared. Okay, anyway, so a couple things. One is if you've got a wheel, one of the things that we often do is we talk about cars going down the road, and we say, oh, okay, so if we want to do the energy of a car going down the road, we say the kinetic energy is 1/2 mv squared. But when we do that, we leave off the fact that we actually underestimate the kinetic energy that the car has, because we don't take into account the rotation of the objects in the car. There's many things rotating: the wheels, the crankshaft, or whatever it's called, the various parts in the engine that's rotating, the things that turn the pistons up and down. And so, for example, the actual kinetic energy of the car is, for example, 1/2 mv squared, which is the entire mass of the car that's moving forward at speed v, plus all the 1/2 I omega squareds of all the things that are rotating. So, for example, there's 4 wheels, so we got 4 of those, and then 1/2 I omega squared of the crankshaft, or whatever, or of the axles, etc. So there's actually a lot more kinetic energy than just the car moving forward. Another thing about rotational motion is that we tend to forget, when we take into account rotational motion, when, for example, you're rolling down a ramp instead of sliding down a ramp, that there's additional torques and that will slow it down. So, for example, if we have an object that is sliding down a ramp, let's even make it a wheel, but let's say that we're not taking into account rotational motion, and the wheel is sliding down the ramp. We know that the acceleration down the ramp we just showed in the previous problem was g sine theta. But if the wheel is also rotating, that moment of inertia, it takes extra effort to get the thing rotating if it has a moment of inertia, if it has extended mass and it rotates. So the acceleration for sliding is g sine theta, but the acceleration is different if it's rotating. If it's rotating, if it's rolling without slipping down the ramp, we're going to have, we have to actually do a little bit more analysis. You have to say, the forces, therefore we're adding friction. So let's draw a free body diagram. We've got the frictional force. If it's rolling without slipping, there's got to be frictional force. The normal force and the gravitational force, mg. So there's an additional force that changes the acceleration of the body. And in order to solve this problem, we have to solve both Newton's second law and for linear motion, and Newton's second law for rotational motion, translational motion and rotational motion. So Newton's second law for translational motion, just take the mg, the component of mg down the plane, which is mg sine theta. We get mg sine theta down the plane minus ff up the plane equals ma. So that's Newton's second law in the x direction. I'm doing this super quick, but that would be the Newton's second law in the x direction. I don't care what it is in the y direction right now. But then we also have to say, the net torque is equal to I alpha. So this is N2, and then this is N2 rotational. Net torque equals I alpha. And so the net torque is going to be R times FF, because that's what's rotating it, equals the moment of inertia of the wheel times alpha. So we have to take this equation and this equation, and we can solve F out of that equation. And remember the relationship between alpha and A, which we didn't write down in this review, but all those variables have relationships, like X is equal to R theta, and omega is equal to, V is equal to R omega, and A is equal to R alpha. So we can take that relationship, and we have to solve all these three equations together in order to find the acceleration, which I'm not going to solve, but you can go ahead and solve it and find the acceleration is going to be less, because we don't only have to pull the mass down the plane, we also have to rotate it. Okay, I think that's a good enough quick review. You're going to have to do homework in order to get through this chapter, and hopefully you'll be able to flesh out some of these things. Have a wonderful weekend.